much better.
Thank you. Sorry that it took a little while. Welcome to the klogW series. Today we are honored to have Gabriel Landi from University of Rochester to give a talk. I'm going to go over a few issues about klogW and GSNP, and then I'm going to pass the floor to Dr. Landi to give a talk. So we always are looking for new people to join GSNP. GSNP is a very diverse community. We have had a very great turnout during the March meeting, and we look forward to more people joining us. You can always check out Engage page and see what we're up to. Also, we would like all early career members to take advantage of this opportunity and submit an image of the month of the recent publication. That would be great because we will have a cycle rolling your publication on the APS website, and we publish one image per month. You can visit our Engage page to see that. I'm going to quickly go through our Zoom etiquette. Please, during meeting, make sure that you're on mute. If you have any clarifying questions, you may put them in the chat, and one of the hosts will pass the question to the speaker. Please save your other questions for the end. After the talk, we would like to encourage you to switch on your camera and post your broader questions either in the comment box or the chats, or let the host ask you, or you can also unmute yourself and ask your questions. And with that, I'm going to pass it to Dr. Landi.
Sebastian is going to introduce Gabriel. To jump in, Sebastian?
Mm-hmm. Just waiting for what she might doing.
Yeah, well, so somebody gets the screen, because I don't know how to unshare from this laptop.
Gabriel, do you mind putting your first slide on?
Yeah,
thank you. And maybe Sebastian, do you want to go ahead and...
Sure. Right. Just briefly, for those who don't know me, my name is Sebastian Deffner. I'm the chair-elect of GSNP. And today it's my great pleasure to introduce our today's speaker and my dear friend, Professor Gabriel Landi. Gabriel got his PhD at the University of Sao Paulo in 2015. Then I was an adjunct professor at the University of ABC before he started his faculty career again at the University of Sao Paulo in Sao Paulo. About 2 years ago, 2023, he moved his research enterprise to the University of Rochester. Gabriel is one of the leading experts in quantum thermodynamics. So I was just trying to figure out how many papers the man has actually published. He has so many that it's a little bit hard to pin down, but it's definitely well north of 80 publications. He's best known for his work on understanding the dynamics of open quantum systems, understanding the thermodynamics of metrological processes, in particular measuring time and other quantities. And he has made significant contributions to entropy production in the quantum regime. Today, he will be talking about information thermodynamics, which means he will explain to us how to understand how information is processed, which means written, erased, and transferred in quantum systems, and how to assess its thermodynamic costs. Gabriel, we're very, very excited about your talk, and the stage is all yours.
Thank you very much. Thank you, Sebastian. It is my absolute pleasure to be here. Thank you so much for the invitation. I'm excited to be able to share a little bit of what we've been doing here in my group in Rochester. And yeah, so maybe to get started. So this talk is about quantum thermodynamics, okay? So I wanted to get started with the following video. Now, the video that I'm going to show is from the Itaipu power plant, hydropower plant in Brazil, where I'm from. Okay, so the power plant has a total of 20 turbines, and the video that I'm going to show corresponds to one of the turbines. Yeah, this is a massive 3,000-ton object, which is rotating 1.5 times per second. It's absolutely incredible, right? And this thing, which would fit into a classroom, is essentially responsible for 1% of all of the electricity produced in Brazil. So it feeds 1.5 million people, just this one device. And the reason why I love this video is because it kind of puts us a little bit in awe, right? So thermodynamics is, and these ideas of energetics, this is so massive, right? So looking at this, why should we bother about thermodynamics in the quantum regime? Why should we care about heat, about work, and all of these things at the atomic level, when in reality, thermodynamics operates at such massive scales? And so this is what I wanted to motivate, right? So why study quantum thermodynamics? Why study thermodynamics in the quantum regime? So to do that, I wanted to showcase this very recent paper that I absolutely love. So this is experiments that were done in Sweden, in Chalmers University, where they showcase the use of thermodynamics to cool down qubits in a quantum computer. So the geometry here that they are working on is what we call in the field an absorption refrigerator. And let me try to explain. So you have three two-level systems. So these three qubits, right? I'll call them hot, cold, and green because I don't know, for the lack of a better name. So the basic idea is that these devices, they're all interacting with each other. And the hot qubit is coupled to a hot bath, the cold one to a cold bath. We all know heat wants to flow from hot to cold. So the natural direction of heat flow should be from the hot down to the cold. But now they do something very clever. It's a trick in atomic physics, which is that they make the frequencies of these two qubits to be very different. So, there's this kind of energy spacing here, which is different from this spacing. In this kind of quantum mechanical setup, processes tend to be very resonant. So because this energy is different from this one, heat actually doesn't flow at all. There's heat, the flow of heat is blocked because of this lack of resonance. And now in comes the third qubit, which is the thing that you actually want to cool, right? So this is, you can imagine that this is a part of a quantum computer, a part of whatever process you're using. And at certain stages in your process, you might want to cool this down, essentially take energy from the excited state and dump it down to the ground state. So what you do is you do a frequency matching trick where the frequency gap of hot plus green is the same as cold. And this allows for this effective three-body interaction where two energy quanta, one in the green, one in the hot, are converted into a single energy quanta in the blue. So by doing this, essentially, if there is an excitation here, so if this system is hot, this excitation will be sucked off by this kind of river of heat flow here from hot to cold, right? And if there's nothing here, then nothing flows. So this is the idea of an absorption refrigerator, where you use two qubits to cool a third one using only thermal gradients. Yeah. So they do this essentially by injecting hot excitations on this one. So it's a kind of an on-demand thing. This bath is not always hot, sometimes it's cold, but if they want the system to cool down, they just inject a bunch of energy here to mimic a hot bath, and then it cools down. So it's kind of an all-demand cooling at the nanoscale or maybe microscale of these quantum devices. And I think this provides a very beautiful illustration of why quantum thermodynamics is relevant, right? Because sometimes we have these really small processes where we need to move energy around. We need to, remove energy from certain places, cool certain systems, or, shuttle energy from A to B, and so on. And so you have all of these thermal processes occurring at the nanoscale, occurring in the quantum domain. And, it is relevant that we try to understand how it works. That other example, it also introduces a very kind of interesting idea. So, what we have there is a little fridge. It's a, kind of quantum fridge. But the process is probabilistic because it's small. right? So it is, we're talking here about microscopic systems. And so everything is probabilistic, which means that every time you try to cool your qubit, you might not succeed. You might actually fail. Now, a success means that, you cool down your qubit, great. A failure could mean that it just doesn't work, right? You don't cool it. Or you can also have what I'm going to call here a complete disaster, which is that because of thermal fluctuations, your cooling protocol actually heats up the qubit. Because, fluctuations are important, this kind of process exists, right? And because things are probabilistic, what you have is that, the probability of success plus the probability of failure plus the probability of disaster have to add up to 1. Right. And then this introduces a kind of trade-off. You might say, well, I want to optimize my machine. I want to, reduce failures and reduce disasters. Yeah. However, there's a fundamental result in quantum thermodynamics, or more broadly in statistical mechanics, which are the fluctuation theorems, the celebrated, Jarzynski and Crookes fluctuation theorems, which says that if a success can occur, then the disaster also can occur, right? And the two of them, the disaster is related to success by an exponential of this quantity, which we call the entropy production, right? And I will talk a lot about entropy production and what it means. But this is all just to say that even though the disaster is smaller than success, because, this is like exponential of a positive number here, this sigma is positive, so it's e to the minus sigma. So PD is smaller than PS. But if sigma is not huge, then they might actually be comparable, right? And so we have to now deal with, not having only cooling processes that are successful, but we have to deal with the fact that disasters are always there. Let me give you another example that will try to motivate why study thermodynamics in the quantum regime. So, as I've argued, as we all know, heat tends to flow from hot to cold. So if you have a hot system and a cold system and you allow them to interact, then with time, both of them will kind of thermalize at an intermediate temperature that is between the two initial ones. Can we break this? Yeah, we can. We can make heat flow from cold to hot. That is actually very easy. A fridge does that. Your air conditioner does that. Right? But if we want to break this direction of natural heat flow, we have to pay a price. We have to use electricity. We have to use work to essentially, allow heat to flow, say, from cold to hot. Right? And this is something that is really embodied in this Clausius statement of the second law, which says that, heat can never pass from a colder to a warmer body without some other change occurring at the same time. So this some other change is the price you pay. There's a fuel that you need to consume if you want your heat to flow from cold to hot. Usually for us, this fuel is energy, it's work, right? One of the main motivations of the field of quantum thermodynamics is that information is also a resource. If two systems are locally cold and locally hot, but they are actually in a globally entangled state, things can actually be engineered such that the heat flows from cold to hot. So the cold system gets colder, the hot system gets hotter. And the price that you pay is that you consume quantum correlations, you consume entanglement. So we participated in this experiment a few years ago, which showcases this idea. This is an experiment with only 2 atoms. Of course, I'm not talking about scalable things here. We're not going to make a power plant out of this kind of idea. It's just a proof of concept. But here is the energy of the hot spin in the case where they're uncorrelated and in the case where they're correlated. So you see that if they're uncorrelated, the hot spin energy goes down, right? Because the hot spin is giving energy away to the cold spin. But if they're initially correlated, then the hot spin will actually heat up even more. And this is accompanied by a consumption of correlation. In this case, is this quantity called the mutual information. And every time heat flows from cold to hot, you actually consume mutual information. So this was a big motivation. I mean, these kinds of experiments, these kinds of ideas have always been a really big motivation in quantum thermodynamics, and these ideas that, you know, information can be used as a resource. So when we think about traditional thermodynamics, it's always this kind of picture that comes to mind, right? We always think about a steam engine converting heat to work and so on. What is emerging from the field of quantum thermodynamics is, in my opinion, a picture that looks a lot more like this. And I kind of wanted to argue in this direction in this talk. Thermodynamics is kind of like a financial theory. Is about transactions, is about, you know, currencies and costs, right? You have budget, which is usually energy, right? That's your budget. You have transduction, which is essentially the transformation of different kinds of energies. And you can use energy, you can consume energy to perform useful tasks. That's just like, you know, taking your money and going shopping. And then on top of that, you have fundamental limitations, which I'll talk about, such as the second law that says that certain processes have a natural tendency to occur. And all of this together means that you have trade-offs, which are central to the field. So trade-offs means, for example, that if you want to improve on something, you actually have to pay the price in something else, and so on. And understanding these trade-offs and understanding these limitations is largely still open questions in the field, and that's the kind of ideas that I want to discuss in this talk. Okay, so to get started, I want to talk about entropy production. So I'll motivate entropy production using classical thermodynamics. The kind of setup that I'll have in mind is a system that has some working fluid. So this is textbook thermodynamics. There's a hot bath and there's a cold bath. And so the processes that can happen is that heat can be exchanged with the different baths. And you can also extract some energy in the form of work. The first law of thermodynamics, it tells us that whatever change in the internal energy of the system, that this change must be related to either heat from the two baths or work. So it's a balance equation. The second law, on the other hand, states that the change in entropy of the system will have two components that are called entropy flows. So this kind of combination, heat divided by temperature, is, according to Clausius, the flow of entropy between the system and the bath. However, the change in entropy is not only related to flows of entropy to other systems. There's another term, sigma, which is strictly non-negative, and it's called the entropy production. It's the entropy produced in the process. So while energy satisfies a continuity equation, a balance equation, entropy does not satisfy a balance equation. You actually have that in addition to flows of entropy, there's some entropy that can be fundamentally produced in the process. Now, the statement that this entropy production has to be larger or equal to zero is the mathematical statement of the second law of thermodynamics. That's kind of a summary. If you want to say, what's the second law of thermodynamics? Sigma larger or equal to zero. Yeah? To understand the significance of sigma, to understand the significance of entropy production, let's play around with these formulas a little bit. And let's think about a cyclic process. So let's think about, you know, the class of processes for which the system goes, the working fluid, this kind of green blob, goes back to the same place afterwards, such that delta U and delta S is zero. So we're going to analyze these two equations when we equate them to zero. The first one, it's kind of intuitive. It just says that work has to be equal to minus the sum of the heats. So whatever, you know, flow of energy happens, work must balance for it. And the second one says that the entropy produced must match the entropy that flows into the environment. So all the entropy produced in the process must flow into the environment. These are the conditions for a process to be cyclic. So let's play around with these formulas. Let's see what they tell us. First, let's imagine that the process that is happening has no work involved. It's a pure heat flow kind of process. So there's only flow from one bath to the other. W is 0. If W is 0, then the first law tells us that the heat from the hot bath must be minus the heat from the cold bath. So energy conservation, whatever leaves this one must enter this one and vice versa. The second law, on the other hand, if we just substitute this expression here, it tells us that there's this kind of product of two things. There's this difference in inverse temperatures times heat. Now, this kind of equality is super deep, and I wanted to just take a second to understand what it means. The second law says that sigma is larger or equal to 0. But sigma is a product of two quantities. So if this product has to be 0, it means that the sign of Q has to match the sign of this thing in parentheses, right? And this is why heat always flows from hot to cold, because the sign of Q must always match the sign of this gradient, or gradient of inverse temperature, let's say. If this flips sign, this one has to flip sign in order to satisfy the second law. And so this is Clausius' statement of the second law. Like we saw, heat flows from hot to cold. Now let's look at another example. Let's say that there is work involved, and let's look at the efficiency if we think about the system as a heat engine. So the efficiency is work divided by the heat of the hot bath, okay? It's how much we get divided by how much fuel we put in. Now, if you just massage these two formulas and substitute things around, you can actually write eta in this way. Very simple calculation. Just substitute the two formulas here in gray, and you can write that the efficiency is actually the Carnot efficiency minus a positive quantity. And this positive quantity is proportional to entropy production. So again, this shows why the efficiency of a heat engine is always smaller than the Carnot efficiency. That's because entropy is produced. If there is no entropy produced, then eta would be equal to eta C. And the more entropy you produce, the lower is the efficiency. So this is another illustration of how this concept of entropy production plays a key role in understanding, thermodynamics and relevant quantities such as efficiency and so on. Now let me talk a little bit about irreversibility and the arrow of time. So here's a little video. There are these famous lectures by George Porter. They're on YouTube, which shows a bunch of videos played backwards, right? It's kind of these fun videos. And kind of the basic question that you want to ask is, why is it that we know that the video is being played backwards, right? We know this is true, but why is it, right? And the explanation is because of irreversibility and because of entropy production. When you can see a video being played backwards, that's because the process is very irreversible. In this case, it's it's a coffee mug that falls to the ground, right? This is a very irreversible process. So you will never observe the kind of the reverse process. You only observe it in one direction because the process is very irreversible. But now let's try to see what happens when we go to the quantum domain. So this is an old paper already 10 years ago now that I did with Draghi Korevsky, who is in Nancy in France. And we played a very simple game. We say, okay, let's have two spin chains that are prepared in a cold, half of it in a cold state and half of it in a hot state, right? We just prepared them thermally. At time t equals 0, we place them together and we allow heat to flow, right? Now, what we observe is that the flow of heat is no longer a deterministic quantity, is no longer just a single variable, but there's actually a distribution of heat flow, right? So this relates to this famous heat exchange fluctuation theorem from Jarzynski and Wycheck, which says that heat flow, or in this case entropy production flow, is a probabilistic event. And what can actually happen is that sometimes you observe negative entropy production. So if you stop the video at some point here, right, you see that there is a histogram of entropy productions, and there's like little regions where you actually obtain negative entropy production. These regions of negative entropy production. They're like local violations of the second law. And they're rare. They are exponentially suppressed, just like when we discussed before this idea of successes and disasters is the same idea, right? However, they do happen. If your system is microscopic, they do happen, okay? And these can actually be observed. Of course, if your system is bigger and bigger, so the different plots here are for different spin chain sizes. You see, if your spin chain is very big, these regions tend to be, exponentially suppressed more and more. So as you go to the macroscopic regime, these local violations, they tend to happen less and less. Another concept that I just wanted to mention very briefly, and this is something that actually started in more of a classical setting, is this idea of what's called the thermodynamic uncertainty relations. Because we have fluctuations now, because entropy production fluctuates, can we say something about the variance of some kind of current? So say you have heat or work in some kind of process, right? On average, it might follow this dashed line. But actually, in reality, every time you repeat your experiment, work and heat are going to be random quantities. They're going to fluctuate. And so you have this kind of spread of your thermodynamic quantities. Can we say something about the variance of a thermodynamic quantity? So usually, these thermodynamic uncertainty relations, they have the following form. They are related to the variance of your heat or work divided by the mean squared. And they say that this noise to signal ratio, it has to be larger or equal than 2 divided by the entropy production. Now, I like this result very much because it says that what's on the left here is something about precision, right? This is noise divided by signal. So it's about how precise you can know a thermodynamic quantity. And what's on the right here is inversely proportional to entropy production, right? So intuitively, we would think that reversible processes that produce very little entropy, are good. But actually, what happens is that if your concern is about precision, then actually the more irreversible, the better. Increasing sigma, right, increases your precision. And for example, I'm sorry that this was cut a little bit here, but there's this very nice paper by Piazzonka and Seifert, where they show that this kind of bound is translated into a bound on the fluctuations of power. So here, this is a heat engine. Eta is the efficiency. Eta C is the Carnot efficiency. P is the power that you extract. Power is the work per unit time. And this is the variance of the power. So what the bound says is that actually there is a bound on the fluctuations of power. And if you try to make your efficiency very close to the Carnot efficiency, these fluctuations blow up. So it's kind of counterintuitive because in thermodynamics, we learned that reversible processes are good and we love to operate close to Carnot efficiency. But actually, if you operate close to Carnot efficiency, your fluctuations might be very, very high, especially in the nanoscale. So you actually want your process to be irreversible to curb fluctuations. And I like this because it comes back to this idea of trade-offs. Very often in thermodynamics, people talk about trade-offs between power and efficiency. This introduces a new dimension to this. It's power and its efficiency and its power fluctuations. You might have a lot of average power, but now you have to think about power fluctuation and so on. So in the microscopic domain, fluctuations are important and you need to take them into account. Okay. Now I reach, per se, the field of quantum thermodynamics. For me, the most important result in quantum thermodynamics is actually this paper by Esposito, Lindenberg, and Van den Broek, which appeared in 2010. I absolutely adore this paper. What they show is how to formulate the entropy production using only information theory, using only information theoretic concepts. So to illustrate the idea, I'm going to consider the following setup. We have some kind of physical system, I'll call it S, which is interacting with some kind of reservoir that I'll call E, some kind of environment. Okay, I will describe this quantum mechanically. So there will be a couple of kind of technical details here, but don't worry about this too much. I just want to say that initially the system and the environment, they're uncorrelated at time t equals 0. And then what you do is you place them in contact and you allow them to interact unitarily. So there's this U here, which is the unitary evolution of both. And afterwards, what you end up with is a correlated, entangled usually, but more generally correlated state of system and environment. And I'll denote this with the prime. So the prime is the state after the evolution, okay? So this describes a wide variety of processes. Our system could be an atom, and the environment could be the electromagnetic field, for example. So this describes many processes in atomic physics. Our system could be a frying pan, and our environment could be the water in the sink. It is actually still described by exactly the same equation. The pan that we're cooking with, is it going to interact unitarily with water from the sink? And the equation is exactly the same. So this describes a very, very broad class of processes from micro to macro. And what they showed is that the entropy production can be written as a sum of two terms, which are terms with a lot of meaning in information theory. The first term is called the mutual information, and is a measure of correlations between system and environment. It describes how the system and environment develop correlations because they interact. And the second term is called the relative entropy and is a measure of distance. In this case, it's the relative entropy between the initial and final state of the environment. So the logic here is that because the system interacted with the environment, the system actually pushes the environment away from equilibrium, right? So rho E is different from rho E prime because the system took the environment away from equilibrium. And so the entropy production can be written as a sum of how much the system becomes correlated with the environment and how much the system pushes the environment away from equilibrium. And these have very operational significance because they essentially describe irreversibility in terms of things that you don't have access to. If you have a system and you have an environment, any correlation that the system establishes with the environment, that's lost. You'll never recover that. You're done. And any, if you push the environment away from equilibrium, that's also something that you cannot recover. The assumption here is that the system is something that you can have control over. You can maybe, apply pulses to your system or whatever. You can do something to the system, but the environment is something that you have no control over. So anything that, flows into the environment, you're done. So for example, if your coffee mug falls into the ground and breaks down, there's going to be energy flowing from the coffee mug to the floor. That energy is gone, right? You'll never recover that. You can still do operations on your coffee mug. You can glue it together. You can, pick up the pieces. So you can still do operations on the coffee mug, but whatever you do to the environment, you're screwed. There's no way to recover that, right? And that's why irreversibility emerges. It's a kind of very operational way of thinking about irreversibility. It's irreversible because there's stuff that you don't have access to, that you fundamentally cannot access. If you could, then maybe you might be able to reverse it, but because the environment is big and inaccessible, you can't.
Gabriel, do we need to know what the primes are on the previous page, or is that?
Right. So the primes just refer to the state after they interact. So if the coffee mug falls into the ground, then
Okay, thank you.
Rho SE prime is just the state after the coffee mug interacted with the floor. It's just kind of the final state.
Thanks.
So let me illustrate a little bit, how this works in the quantum regime. So imagine you have an atom, I don't know, like the hydrogen atom, and it has many energy levels, right? And you allow it to interact with a thermal bath. For the atom, usually the thermal bath are the photons, right? So if you put your atom in a pizza oven, it's going to be absorbing and emitting a bunch of photons into the pizza oven. And that is the process of thermalization. So if you happen to prepare your atom in some sophisticated state, and you give it enough time, we expect that it will eventually thermalize. Thermalization is a process involving the exchange of energy, right? So it's essentially, the populations of your energy levels that will adjust to the populations that the bath wants. In addition, however, there's also the process of decoherence. If we were to prepare a state that is some kind of superposition of energy levels, because the system is interacting with this bath, after some time, it will actually lose this coherence and become essentially a diagonal density matrix. So some kind of pure state like this, for example, is represented by a density matrix like this. And decoherence is the process that takes a density matrix with off-diagonal elements to a density matrix with only diagonal elements. Yeah. So you see there are two processes going on here. There is the adaptation of populations. A squared becomes P0, B squared becomes P1. This is the thermalization of the energy levels. But there's also the dampening of coherences. A, B star goes to 0, right? So you have these two processes going on. And one of the things that we showed a few years ago is that actually the entropy production can be split into two contributions. One being the entropy produced due to changes in population, and the other one is the entropy produced due to the loss of coherence. And this is pretty cool because it means that if we happen to start with these populations being exactly like these ones, but still with coherences, we could have a situation where there is loss of, there's dissipation of information without dissipation of energy. And that's very interesting. In classical processes, dissipation is an energetic concept. But here you can actually have, without any change in energy, you can still have dissipation in terms of loss of information. The other result that I wanted to get back to is this experiment that I mentioned about consuming correlations to make heat flow from cold to hot. Remember, we discussed how the entropy production for heat flow was the product of these two things. There's the kind of the gradient of temperatures here, and there is the heat. And before, what we had was that sigma was larger or equal to 0. However, if there are correlations present, if initially the state of the two systems is actually correlated, this result has to be modified. This was first shown in these two papers here by Partovi and Jennings and Rudolph. And what you get is that actually the product of these two things has to be larger or equal than the change in mutual information. This is the modification in mutual information, so the change in correlations. And so this is the bound that establishes to us this fundamental idea that information is also a currency. Because if we want to have heat flow from cold to hot, we need to consume correlations. We need to have this thing negative. If delta I is positive, the bound just says that the product of two things is a positive number. So these two things must have the same sign. But if this thing is negative, then we have the product of the two things can be negative, which means that you allow for heat to flow from cold to hot. So if you consume correlations, you can actually break the second law. Just like if you were to consume, say, energy in your air conditioner, you would also do the same thing. A third example of entropy production and kind of interesting things that come out of this is what happens in quantum optics. So in quantum optics, you have these optical cavities, which essentially you inject photons into. So optical cavities are just like two mirrors, and you inject photons with a laser, but the photons can leak out of the cavity, right? And this process of photon leaking is essentially a zero temperature process. If you talk to any quantum optician, they would be very comfortable to model this as a zero temperature process. But now if you go back to the second law and you stare at this for a second, it's kind of weird because the second law says that you have this 1/t everywhere. And if t is 0, what do? You have that the entropy production is infinite. It's kind of a bug, right? But the resolution to this bug is because this does not include vacuum fluctuations, which are present in every measurement. So one of the things that we showed was that essentially the entropy production in an optical experiment has to be modified to include also the vacuum fluctuations. So there's an effective temperature, which is the Bose-Einstein distribution plus 1/2. And at zero temperature, n bar is 0, but we still have this 1/2, which are the vacuum fluctuations. And then we recover the usual second law. So since I'm noticing that I don't have a lot of time left, let me just quickly skip these two slides. And let me go now to more recent work, which we've been doing here in Rochester. I wanted to mention the work that my PhD student, Abe, did in collaboration with Patrick Potts from Basel University in Switzerland. So it's kind of interesting. So this paper was published today in PRL. There's also another reference about continuous measurements that kind of started the whole thing. So the question that we wanted to ask here is to kind of go back to this notion that I started in the very beginning about, processes that might fail, that might succeed, or that there might be disasters and so on. So we're looking at specific systems. The system we have in mind is what's called a double quantum dot. So these are two dots that can fit one electron at most. And they're coupled to two baths. There's a hot bath and a cold bath. And so the process is such that there are four things that can occur. You can either have an electron tunnel from the left to this dot, or out, and then here in or out from this bath. So you have four possibilities. And the way they do these experiments with quantum dots is they have a little sensor that they can actually monitor these specific tunneling events. So they can monitor the kind of the individual tunnelings of each electron, right? And so what the kind of data that you get from their experiments, it might look a little bit like a string like this. You can actually reconstruct these strings from experiment. The string is a sequence of symbols that represent if there is an injection or extraction of an electron, and if it came from the left bath or the right bath, so the hot bath and the cold bath. So it's a symbol that has four possibilities: IH, EH, IC, EC. And now, kind of the game that we were playing is, okay, can we stare at strings like this? Just look at big strings that we might get from experimental data. And can we identify thermodynamic processes? Can we identify the idea of thermodynamic cycles just from looking at these strings, right? So why do we want to do this? Well, I mean, let's consider some simple processes here. So imagine you have an electron that is injected to the hot bath and then extracted to the cold bath. I mean, this is clearly kind of a work engine-like situation, right? Because heat is flowing from hot to cold, and in the process, you actually extract chemical work because you create a chemical potential gradient in the process. Or you could have the reverse effect, the reverse process, where an electron tunnels from the left to the dot and then to the, from the right to the dot and then to the left. And this is like a cooling process. This is like a refrigeration, right? Because essentially we just shuttled energy from the cold bath up to the hot bath. And so you can only do this at the expense of chemical work. In addition, however, because things are stochastic, because things can fluctuate, we also have silly processes that don't really lead anywhere. We call them bounces, or idle cycles. You can have, for example, an electron that tunnels from the hot bath and then back, or from the cold bath and then back. So this is a hot bounce and it's a cold bounce. Bounces are processes that don't really do anything, right? So if we go back all the way to the beginning where I was talking about, success, failure, or disaster, if what you want to do is, refrigerate your machine, then this would be success. These would be failures, the bounces would be failures, and the engine would be the disaster, right? Because you're trying to cool, but you actually heat it up. And so the question is, can we identify these cycles only by looking at these strings? So the first thing that Abe showed is that actually there's a subtlety here concerning, the fact that you might be able to have more than one excitation. In principle, you could have one electron here and one electron here, and these electrons are indistinguishable. So in principle, you might have a string that looks like this: inject cold, inject hot, extract cold. Now, what does this mean? What does this block mean? Does this mean inject cold, extract hot, inject hot, extract cold? This would be a cooling cycle and a engine cycle kind of intertwined? Or does it mean inject cold, extract cold, inject hot, extract hot, which would be two bounces, two idle cycles. Because electrons are fundamentally indistinguishable, it's impossible to know. So when you can have multiple excitations inside your machine, it's impossible to identify what are the individual thermodynamic cycles looking only at these strings. So the first thing that Abe showed, this is a little bit more technical, is that if you consider this class of master equations, which called as Lindblad master equation, there's Abe proved this theorem about what should be the structure of Hilbert space if you want to be able to identify cycles. And essentially, the idea is that you can at most have only a single excitation inside your system. So every time you inject a particle, your system must go to one corner of Hilbert space. Every time you extract, it must go to another corner of Hilbert space. So this is what's called the post-injection and the post-extraction. And again, this is a little bit technical, but these are just the kind of the structure of all of the elements in your density matrix. So I'm not going to go into the details about this. I just wanted to say that once you assume that there can be only a single excitation in your process, then you can only have injections followed by extraction. So your string of data is always going to look like IE, IE, IE. But there's still like, unknown about what's the little bullet here. Is this a hot or is this a cold? So then you have these four possibilities only. Engine, refrigerator, hot bounce, cold bounce. These are the only four possibilities. And we call these cycles, because we're not very creative, we call them cycles 1, 2, 3, and 4. And once we establish this, then this is really the beauty, is that now we can answer many new questions that we couldn't answer before. We can ask probabilistic questions such as, what's the probability of a cycle being of a given type? How often does this cycle happen compared to this cycle, and so on? And there's also time involved. So what's the probability that this cycle takes a certain time tau? Or what's the probability that this cycle takes a time tau, and so on? What is the average time that each cycle takes to complete? We can even ask more sophisticated questions, such as how many bounces usually happen between successful cycles? So it gives us a notion of intermittency. Very often, your machine might actually just be doing something useless. It might just be bouncing around, right? But every once in a while, you actually do something useful. It's exactly like a pinball machine, right? In the pinball machine, most of the time, you're just pressing the button and the ball is just running up and down. It's not really doing anything. But every once in a while, you actually score something. And so you do something useful. What is the probability that it takes 20 bounces between two useful cycles, and so on? So we can ask all kinds of statistical questions about individual cycles at the level of these quantum trajectories, which I think is pretty cool. So again, I'm going to skip over the details. Let me just show you a little plot. This is what we call a 3-level atom. So this is an atom that can have 3 levels, 0, 1, and 2. And the rules is that there's a hot bath, which allows excitations to go from 0 to 2 or 2 to 0. And there's a cold bath that goes from 1 to 2 and 2 to 1. And there's also a kind of unitary drive here that allows the system to oscillate between 0 and 1. And so this kind of system, it describes the double quantum dot that I was mentioning before, but it's also broader. It also describes a maser, right? This is called the 3-level maser in atomic physics, for example. And so I won't have really much time to talk about all of the kind of different quantities. I just want to flesh out this one. This is the probability of different cycles to happen. And this is in the regime where, on average, you have a refrigerator, and this is in the regime where, on average, you have an engine. And so what we see here is that, let's take refrigerator, for example. We see that actually the most likely process, the most probable one, is a cold bounce. It's x = 4. So the most likely thing that can happen in a refrigerator regime is just boink, boink, and nothing happens. The second most likely is a cold cycle. It's x = 2. So it's the process where you absorb a quantum from the cold bath, spit it out in the hot bath, and then come back here, right? And then you have the hot version, so the engine and the hot bounce here. As soon as you cross over to the engine regime, you see that the whole scenario inverts. Now, what's most likely is a hot bounce or an engine cycle, and the cooling and cold bounces are less likely. The other thing that I just wanted to mention are these two quantities, which are measures of intermittency. Intermittency is something that's still kind of a work in progress. It's something that we're trying to characterize. But the broad question that we want to ask is, how often is your machine actually doing something useful? These are stochastic machines. Most of the time, they're just doing useless stuff. So, the quantity in red here is the probability of your machine doing bounce 3 and 4 divided by the probability of it actually doing a useful cycle. And you see that it grows significantly when you're deep in the engine regime or deep in the refrigerator regime. It's actually, you know, quite likely that you get bounces. What's plotted here, on the other hand, the blue one, is the time it spends doing useless things. And I just wanted to highlight this because, you know, the questions are different. This is how often it does something useless. This is how much time it spends doing something useless. And because each cycle takes a different time, they're actually different. So we see that, for example, both of them have kind of like somewhat of a similar behavior, but you see that deep into the engine regime, for example, things tend to be very fast. So actually, the time it spends doing something useless is not as big as in the cooling regime. Yeah. Okay, so this is pretty much all I had to say for now. Let me just conclude. I mean, this talk was about entropy production and this idea that it quantifies irreversibility. What I try to show is that when we go to the quantum domain, irreversibility characterizes a lot more. There's this information theoretic approach. You can use entropy production to characterize loss of information, the role of quantum correlations, zero temperature fluctuations. And I didn't talk much about measurement back action, I apologize. And towards the very end, I talked a little bit about this idea of extending thermodynamics to individual quantum trajectories, to individual cycles within a quantum process. And I want to leave you here with a couple of review articles that I've wrote on this. In particular, there's this third one, which is very recent, about current fluctuations, which is essentially a tutorial kind of article. So if you want to learn more about how to describe current fluctuations in the quantum regime, we try to make this as a very pedagogical paper. So that's pretty much all I had to say. Thank you very much, and I'm open for questions.
Thanks very much, Gabriel. Very nice talk. We have time for questions. I'm very sorry I missed one of the questions when halfway through. Would Julia and Rincon want to unmute themselves and ask the question? There's a question that says, how can one understand that those relations are actually quantum? Would the person who asked the question want to?
I think I see the question here. Oh, sorry. Yeah, Julian, which relations do you mean?
If he's not.
Maybe I can ask.
Yeah, maybe we go to the next one.
Petrat, yeah.
Yes, please.
The answer is very simple. No, so this form of the entropy production is not still true if they're initially uncorrelated. It does assume that they're uncorrelated. There are these papers by Partovi and Jennings that they do discuss. It's a little bit different formulation and so on, but they do discuss a little bit what happens when things are initially locally correlated.
There's a question from John Delos. Would you like to unmute yourself and ask the question, or?
Yes, okay. in your next to last slide, you seem to show that if the hot reservoir over the cold reservoir, the temperatures is less than a factor of 4. It has to be very much hotter than the cold reservoir, or else it will act as a refrigerator. But am I understanding that correctly?
Yeah. So the what determines this kind of special point where it kind of switches operation is actually the frequencies, the energy frequencies here. So the number 4 is actually somewhat arbitrary because it depends on the gap between 0 and 2 and between 1 and 2. I don't think, we wrote it down here. So it's like TH over TC is omega H over omega C. So by playing around with these gaps, we can actually change this 4 to be kind of any number we like. Is this like what you're wondering? Yeah?
But that T is temperature.
Yes.
Okay.
What's the concern? I don't get it.
Well, it seems unusual to have a hot reservoir very much hotter than the cold reservoir, and nevertheless the thing is acting as a refrigerator. So I just thought perhaps I misunderstood.
Oh, I see. Yeah, so that's kind of what I mean. You don't really need to have the hot reservoir to be much higher. So we could have TH over TC to be 1.1 if we wanted. We just have to adjust the frequencies.
Thank you.
Yeah.
There's a question asking about whether these ideas translate to quantum computing.
I don't think I have a strong answer for that. No ideas on quantum computing. Yeah, especially not AI.
Maybe I could ask a question. So hi. Just my intuition would be that at low temperatures, there'd be more probability of 2 particles hanging out. Or as you get more quantum, somehow there'd be more probability of, I mean, you've separated it out into when you can't have 2 particles and when you can have 2 particles. Would it be fair to say that the sort of more quantum you are, the more chance there of indistinguishability playing a role, or overlap becoming more important?
Right. So you mean about this drawing, right?
Yes. And when you said we have to separate the Hilbert spaces out and move on from there, basically. Right?
Yeah, sorry. So maybe, I apologize. I think I was a little bit rushed towards the end. But so in principle, you can have models that can have many particles, right? However, what really actually matters here is for these double quantum dot setups is Coulomb repulsion. So these are electrons that you put in, and these dots are very close to each other. And so depending on how you design your double quantum dot setup, you might have what they call a Coulomb blockade or not. A Coulomb blockade means that, the energy cost to just putting a second electron there is huge. And so effectively, there will always be just one electron in there or not. But if the dots are kind of further apart, or if they're very big, you might actually have more than one electron. So the idea is that, there's a class of models or a class of systems which have only a single excitation. And the argument that we make is that for this class of systems, we can draw some conclusions on the thermodynamics of individual cycles. Does that make sense? Yeah, thanks.
Hey, can I ask maybe 2 questions?
Yeah.
The first is that does your series work help with the measurement problem interpretation about it? The second question is, can your work be applied to high-energy quantum antibody system like quark-gluon plasma, which is both quantum and thermal, and a little bit, and also hydrodynamic? Yeah,
so those are great questions. If my work helps with the measurement problem, it's something that a lot of people in the field of quantum thermodynamics are interested in, in connecting the 2 things. Of course, the measurement problem is still open, but some of these notions of irreversibility, they definitely connect to the measurement problem, or more broadly, actually, they connect to the notion of thermalization of isolated quantum systems, right? Why is it that an isolated system will spontaneously thermalize? And I don't personally work on any of that, but there's people that are interested in it. Yeah, so that would be my first question. It's like, yeah, I mean, it does help, it gives insights, but of course the measurement problem is still very much open. About high energy, you're absolutely right. So all of these ideas actually do apply there. What characterizing some of these quantities might not be easy, right? So for example, how would you measure entropy production in that kind of process? For instance, it might not be easy because in high energy, you don't really detect, you cannot really do any kind of measurements you like. You only measure, you know, scattering experiments. But the ideas still hold. And I've had several discussions with people in high energy. I don't know if there's a lot of people actively trying to connect the two things, but it's definitely something that is kind of a low-hanging fruit. Yeah.
Thanks.
Yeah.
I ask a really naive and naive question. You couched all of this in the familiar language for us of, you know, a T hot and a T cold, Carnot efficiencies. Is when systems are entangled, is there just a conceptual difficulty in defining T hot and T cold, and are these independent quantities?
Yeah, yeah. So that's a good point. So if you think about a state like this, right? This is actually kind of a fascinating idea, right? The idea is that when you think about hot and cold, it's like a local thing. It's like you locally look there, and it seems hot, it seems cold. But if you then take a step back and you look at both of them together, you will actually learn that they are correlated, right? This is not quantum, by the way. I mean, the same idea, we could do it classically as well. You could have two particles that are correlated. They wouldn't be entangled per se, they would just be correlated. But you can still have kind of similar ideas for classical particles, right? So it's more about like, you know, locally they're thermal, but globally they're not thermal.
And you would, to define the temperature, you would just do the local measurement.
Yeah, yeah. So we would define the temperature by saying, you know, it makes sense to define the temperature if locally you look at the state of this thing.
You look at just ensemble statistics locally, and
yeah.
I see. Thank you.
Yeah, absolutely.
Folks, are there further questions? If not, this may be a good time to thank Gabriel again for a very nice talk.
Very much.
Thank you very much. And the talk will be available in a few days at this website if you want to share it with friends and family.
Yeah.
Okay.
Thank you for the opportunity again. Thank you for the invitation.
This was great. Thank you so much.
Bye.
Thank you.